All right, so we should be back. We're streaming a different problem now. Hello and welcome. Just give it a moment the system to kind of wake up. All right, so yeah, there we go. Nice, we're here. Hello. So didn't really take much of a break. Just kind of went right into it. I did want to comment something though. Quickly. So welcome everybody. There was one comment by Simon that I missed. I also this is related to the previous question. Unique word abbreviation. Yeah, this one. Also pondered hashing the actual words to avoid storing them all and doing a lexicographical compare, but that would have been cheating. Hashing the actual words, hash the words to avoid storing them and doing a lexicographical compare, but that would have been cheating. How does it sound like it would have been cheating if you could have pulled it off? I don't know how you would have done that. Well, hashing words to avoid storing them all. Oh, actually, yeah, it's pretty interesting. You can do a, yeah, the words are small enough. They don't have so many, they have a small number of characters. You can actually consider them to be like numbers and then hash those numbers. And then store the hashed number, I guess, instead of the word. Yeah, lexicographical compares are definitely awkward. Technically, that wouldn't have been cheating. Although, I think at that point, you might as well just have like a hash map of strings or something like that, if that makes sense. Or a hash set, maybe. No. What would you do? I think I might like be defeating the purpose at some point. Possibly. No, it's not. No, it's basically just a hash key for the string. That's interesting. I didn't think about that. Anyway, let me, I think I have to think about that some more, actually. I think the only problem you would run into with that is, yeah, because you don't want to store all the strings. You want to store hashes of the strings. Like that is actually better instead of for the comparisons. That is actually better. But the problem with that is you could have collisions, and that'll make things really confusing. Unless you had a unique hash for every word. Well, the words are small enough where you probably could have a unique hash. Like you could literally do it's 20 characters. Each character is only 26 characters, right? So it's like a hexadecimal number, but with 26 characters instead of, basically, yeah, you can convert, you could consider these strings that have 20 characters, consider them to be like base 26 numbers and do it that way and convert from base 26 to base 10. Hopefully that fits in a long, although base 26 is pretty big, right? Like 26 to the 20th, I don't think fits. Whoops. No, never mind. That's really big. I take that back. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's kind of, never mind. That won't fit. I don't know what you would do, actually. I don't know. I'm not very good when it comes to hashing. To be perfectly blunt with you. No, I probably would just do is what I did. I'd probably just store the strings as they are. You could in theory, come up with a hash key, a hash for the string, but the problem with that is it could be very, I could have collisions, and the problem with the collisions would be you don't actually have a way to resolve the collisions, really, right? Because all you have stored is the key. You would probably need to like store a mapping of the keys back to the strings anyway. That would speed things up, though. Yeah, if you have a if you only if you I don't know. It would store things. It would speed things up for like a certain number of cases, because only when you have a collision or potential collision. How do you even know if you have a collision, though? Only if you have a potential collision, I guess. Then you have to check. Check that hashed value against what it's actually supposed to represent. These hash keys, compare them, or compare what they're actually supposed to represent to each other. So you still need to store everything anyway. Yeah, you don't really get too much benefit doing that, actually, because if you're going to go into, well, technically, I don't know. Yeah, because then how do you make sure you have the right word anyway? Yeah, I don't know. I don't really like it. I don't know. I don't really know I'm not very good when it comes to hashing strings. That's like not something I'm super comfortable familiar with. Storing the hash instead of the string, because you could run into collisions. 20 lowercase letters are just shy over 94 bits of information. Yeah, but then I guess you need what? I guess you need 2 integers, I guess, for excuse me, 94. Well, wouldn't 20 lowercase characters be 8 characters each? Or 8 bits each, right? How did you get 94 bits? Character is, unless we're only using 127, right? That's 7 bits, right? Oops. Yeah, it's 8. Yeah, 7 bits would be. I think I see why. Wait, no. How did you get 94? Log 2620. Oh. Oh yeah. Oh, okay. Fair enough. Right. That actually does make sense. It would be actually 2621, I think, right? 2621 minus 1 over 25. I think that's actually the number. But we do log 2, so do log divided by. Well, no, I'm sorry. No, 20. No, you're fine. I'm sorry. I take that back. 26 to 20 is fine. I'm sorry. But log divided by log 2. Yeah, 95 bits. So 95 bits. Yeah, if you do right, consider that. Yeah, okay, that's fair. That is better actually than 120 bits, 140 bits. But the problem with that is you need, I guess 2 integers then. How do you hash 2 integers? Just thinking, how do we? How do we do that? Wait a second. So the number, okay. So basically we're going to use very large integers, very large width integers to store the value. And you can use a bit set to do that. A 95 bit array, size 95 bit array, and just do the algorithm normally. The normal algorithm is right. You just take whatever the number is, divide by 2, take the remainder, and then push those bits down. I think that's the typical way to do it. The only thing you put it, I guess you could put it into a stack. That's probably easier. That's usually how I would do it. You do, yeah, keep dividing by 2. How can you interpret the character array as? How do you interpret it as numbers? I don't know if it's even. I don't know if it's even. Well, 26 is even, right? So you can just and, you don't need to, or you just determine whether or not what the remainder is. You don't need to. Well, actually, no, you do need to divide by 2. How would you do this though? I'm just thinking converting from base 26 to base 2. How do you do that? That's a good question. For me, I'm thinking like, well, you just convert it to base 10 and then just divide by 2 a bunch of times, because I know how to go from 10 to 2. But actually, really, you can go from 26 to 2. It's 2 is b, right? Would be b in so you quote unquote divide by b. What does that even look like? So division is just the opposite of multiplication, right? You just multiply b by a certain. So you can, in theory, you could redefine a multiplication table for 26 base multiplication table, and then redefine division over base 26, and then every time you divide by b, you take the remainder. You would get basically 0, 1, or a or b, and then depending on a or b, you can map that to 0, 1 in a bit set. I mean, that's one way of doing it. Redefine multiplication with a new multiplication table, so that we are using base 26 operations. So we don't need to. That way you don't need to like try to convert the string into a gigantic. Try to convert the string into a gigantic. Like basically try to convert it to base 10, which would require a huge number of bits. Something like that, or like, yeah. I don't know if that would require a huge number of bits. I don't know. I actually don't know. I don't know. I don't know if that makes sense to redefine. I don't think that makes sense to redefine as a base 26. I don't think so. I don't think that makes sense. By the way, that's a lot of operations. 26 by 26. It's 200. It's quite a lot. It's a lot more than 256. That's no. 25 times 5 is 225. 25 times 25 times 25 times 25 is over 1,000. It's 1,225. So that's way too much to do by hand. Calculation is wrong though, multiple ways. For one, not every word is 20 characters long. So it's actually even more. No. That's not. This sum, 26 raised to the 20th. This is a geometric sum, right? Which is no. I'm sorry. It's actually, you know what? I did it wrong. It's this. This is the right one. I'm sorry. Yeah. So, well, no. It's, you know what it is? Okay. The geometric sum would be, it's s raised to the n plus 1, 1 minus 1 over quantity s minus 1, or r if you want, not s, r. So it's 26 raised to, we have 20 of them, so it'd be 21 minus 1 divided by 25. But the problem is that's if every character is maxed out. Like, we need enough bits to store this number. Which is, oops. Okay, yeah, all right. It's still fine. We still have enough bits. I think actually you're right. I think I had it right the first time, and then I got it wrong the second time. But it's roughly the same. I mean, it's very similar. It's very close to just 26th to 21st. Oh no, wait. Oh, I'm sorry. No. Wait. No. It would be 22 then, right? Because we're getting the sum up to, wait. From 0, I equals 0 to 20. Yeah, it's very close to 26 to the 20th. It's very close. And on the other hand, the abbreviation stores some of the data already. So to the 26th to the 18th, in the worst case of length 20, this will also fit all the lower lengths. Well, no, this one we actually are storing the word itself, not part of the abbreviation, right? Or I guess what you're saying is that we wouldn't match the abbreviation unless the first and last characters were the same. We get into some hot water with that because of the strings that could be single characters. Although that doesn't matter too much, right? Because we can hash. We can just. I guess we could for single characters. Oh no, actually that's fine. No, we have enough bits for that. We wouldn't strip the first and last characters from. Yeah, we don't want to strip the first and last characters, I think. I don't know if we want to strip the first and last characters at all. We only want to strip the first and last characters for. I don't know if we want to do that at all, actually. I'm thinking about it. Because if we're trying to match the well, I gotta think about that for a minute. If they match the other hash, that means the first and last character should be the same. So now we just need to match the second hash, the other hash, which would strip the problem with that is you could have, if you're storing these hashes, it doesn't work properly because you could have like AXA, right? Or make up words, but if AXA was, we store that in our hash set saying that this is in the dictionary. That's just X with A stripped. If we try to compare another word like BXB, it's going to show that, oh, this does exist in the dictionary. Even though it could be, AXA and AYA and, BYB or something. Like, in other words, you can get in the hash you can get the hash value, but it's not there because you have a something. It could be a different word that you have. You could have like AYA is your abbreviation, or no, AYA is the word you're looking at. BYB is in your hash, and then AXA is how you got past the first filter, right? The A1A, if that makes sense. That's how you got. So in your dictionary you've got two different words. There's an AYA and then a BYB, and then you're looking for AXA or AX. You have you have BXB and AYA, and you're looking for AXA, and the AYA will say, oh, there's something in there, take a look, and now you match the AXA against the BXB incorrectly. So I think you do. I think you do need. I think you do need both of the characters for that hash. Two 26 less than or equal to 32, so 5 bits suffice to store one character. 5 times 18 equals 90, and no weird multiplications. Ah, good call. I didn't think about that. Yeah, that works. That's good. Okay, 90. Yeah, 90 bits would be better. Right. Oh no, but that's 18. You want. I still think you need 20. But no, that would give us. I think 90 is better than. I mean, 190. Either way, I mean, we do need a larger width integer, but we can use a bit set. I mean, however we do it. I mean, the easiest way to do it probably actually would be just 8 by 20, right? That's probably the easiest. Is just say forget it, go with a bit set of 160, and I think you can hash a bit set, and then just dump it all right in there as it is. Like that's a pretty good hash already. You know, it's already better than that's already a lot better than well, actually, I don't know, man. I mean, at this point, why wouldn't you just store the string? You know, because storing the string is basically is same amount of data, right? I guess technically you could do some funky stuff to go into 95 bits or 90 bits, however many bits we needed. I think it was 95. But and actually I was talking about that I did the calculation wrong because I only had 26 to the 20. That's my start value. Oh, okay. Word comparison is done only after the abbreviation is successfully matched. So AXA goes AA1 hash X, AYA matches AA1 but not hash X. No, but see the hash for X could already be present in your dictionary. So what I'm saying is, let's say you have AXA and you're looking for BXB, and you also have BYB, right? So BYB has BB1 in your, so you have BB1 in your what do you call that already? The dictionary. You have BB1, and then you also have AA1. So any of AXA, ABA, or AXA, AYA, or BAXA, or BYB will pass, and then because you had AXA and BYB already put into your stored as strings in your hash, the hash for X will show as a string that is in your dictionary, if that makes sense. So I guess what I'm saying is you would what you're trying to avoid doing is comparing every string in the dictionary that matches that particular abbreviation, all of those strings, you don't want to store all those strings to compare them lexicographically against this word that you're looking at now that shares the same abbreviation. So you'd want to store the hashes of these values, of these strings. However, you could end up with a problem because the hashes could match for that particular abbreviation, but it doesn't. It's actually the wrong. Actually, maybe I'm wrong about this. Hold on, wait a second. I gotta think about it now. Maybe I'm wrong actually. BXB would match hash X, but fails to check against AA1 already. Right. Yeah, actually, maybe I'm just wrong about that. I'm trying to think about it. I'm like, wait a minute. Yeah, because I think you're right. No, I take it back. I think you're right because the hashes that you're going to be comparing against the string, it's not going to be a total list of the hashes. The hashes are going to be separated by the actual what do they call that? The abbreviation itself, right? They're all linked to the abbreviation, so the only way you access them is if you pass that abbreviation in the first place. Okay, I think you're right then. I take it back. I take it back. I was kind of confused myself, or I missed a detail. Yeah. But thank you for that. So actually, you're right. Yeah, you could use 2 less then. You could use two characters less. Well, I think at that point, I mean, realistically, if we only need 160 bits anyway to store it lexicographically, then we might as well just do it that way. Might as well just use strings. It's not. I mean, you're saving a little bit of space, maybe a little bit faster, but already you're getting into some funky stuff because now you need to use comparisons for basically extra wide. Effectively extra wide integers, I suppose. So I don't know. Pretty interesting though. Let me go to the next question. But yeah, I'm glad we talked about that though. Thank you. That was interesting. That was interesting. So I'm not really sure though. I'm not really sold on the hash. I feel like I would need to see someone put together. I don't want to say put together. I don't really need to see it, but I'll just say I'm not really sold on the hash. I'm like kind of meh about it. I'm not sure how I feel about it. I think in theory you could do it, but it would be. I don't know what I would do to actually do that. I think. Excuse me. I think literally converting the characters directly to a 160-bit, or 100. What do you say with 2 less characters? It'd be 150-bit. 150-bit bit set, and then hope that. Actually, no, I don't think you need to be able to hash the bit set. You just match the bit set. That's all. You just hash and hash. Yeah, no, that's fine. So you don't need to have a hash for the bit sets. But you do 150-bit hash bit set, or do some fancy maths, quick maths, and do your what do you say, 20 to the 18th? Oh, let's try that out. What does that give us? 20 raised to the, it would be 20 to the 19th minus 1 over 18, which is, I'm sorry, 26 to the 18th to the 19th plus 1 over 25. No, what am I doing wrong here? It's 26, the geometric sequence, right? 26 raised to, it's 26 raised to, we want to go to 18, so we go plus 1 is 19. 26 raised to the 19th minus 1 over 25. There we go. Okay. Now we take the log of that and then divide by log 2. Is the log of this divided by 25? How did I get that? What happened? Why did I didn't hit the equal sign? Whoops. Didn't mean to do that either. Okay, that divided by log 2. Okay, 85 bits. All right, fair enough. So we could do some maths to get 85 bits. And that would be our hash, and basically just convert that to base 2, from base 26 to base 2. Yeah. Well, basically you divide by 2 each time and take the remainder, throw that into a stack, and then reverse the stack. But how do you divide by 2 at base 26? I don't really know. Now you could do. No, wait. Yeah, I don't know. So I'm still kind of hung up on that. Sorry for sidetracking on the hash cheat. I wouldn't call it a cheat. I would say it's actually just another approach. But no, it's not a big deal. I'm just actually, no, because that's an interesting question. Like in theory, I should know how to do that, right? That's why I'm thinking about it. It shouldn't be this difficult for me to think about. I want to say. I'm just thinking here. The bits and the bit sets. How would you divide by 2? How would you do that? Convert it to base 2. Yeah, like I said, converting to base 2 from base 10, I just keep dividing by 2 and taking the remainder. But how do I, like if I wanted to convert from base 16, well base 16 to base 2 is pretty straightforward, but base 16 to like base 10, that's kind of more like what we're working with here. And excuse me. Maybe you can convert from 26 to 16. Maybe that's better. But how do you divide by anything and get the remainder when you're dealing with base 26? I guess that's what you gotta think about. Like, how do you even? A really big number in base 26 that doesn't fit in any of the registers, or it doesn't fit any. I mean, you could in theory create like just a big integer, right? Using like a big integer library, and then put it into a big integer, and then convert that big integer into a bit set. Now here's the thing about that. Now you got to think about the runtime efficiency of converting your word that's a string into a big integer, performing the change from the big integer into a what do they call that? A base 2 bit set, which is technically a base 2 big integer. Yeah, converting that to basically a base 10 big integer. How many bits do you need to store a digit? I think you need 4 bits to store a digit, right? So 2 digits per character, 2 digits per 8 bits. Just thinking about the last time I implemented a big integer. I guess you do want to use, if you're going to use big integers, you actually want to use hexadecimal characters, convert it to base 16, operate in base 16. So that way you can make more use of the storage. Should be faster. Basically each segment will be a hexadecimal character. That would be, a hex character is 2 bytes, or 16 bits. No, a hex character is 4 bits. So never mind. Yeah, it actually doesn't. Excuse me. Oh, maybe you do. Yeah, maybe you do. You want to operate in characters, so you would use hex values, which would be really two. The pieces would be two. Yeah, the hex word would be 16 bits. Or no, each character is 8 bits, and the hex value is 4 of those bits. So you'd split every character into 2 pieces, to 2 hex values. So you'd have a vector of characters, and each character represents the next 2 hex values. And you'd convert everything to basically base 16 big integer. And then you can convert that pretty easily to base 2 bit set. Anyway, that's just thoughts. From back to front, if current digit is odd, add 13 to the previous digit, then divide just the current digit by 2, rounding down, dividing by 2 in base 26. Yeah, is that how you do it? From back to front, if the current digit is odd, add 13 to the previous digit, then divide just the current digit by 2, rounding down. Wait, so the way you divide by 2 in base 10 is you'd find out, is it odd? And that's the remainder, right? Odd or not is the remainder. And then you would shift all the bits in the bit representation to the right. No, you would, what would you do? We divide by 2. What happens when you divide by 2 in base 10? Well, you take every digit from left to right, and you figure out how many times does 2 divide that particular digit. And then if it doesn't divide that digit, so if it's like a 1, then you increase that value and shift to the right a bit. You have like a carryover rounding. Now, dividing by 2 in base 10 is kind of complicated. It's kind of complicated. I don't know, dividing by 2 in base 26 is probably similarly complicated. The current digit is odd, add 13 to the previous digit. From front to back. By front, do you mean like the most significant bit or the least significant bit? From back to front, I'm assuming the least significant to the most significant. If it's odd, add 13 to the previous digit, then divide just the current digit by 2, rounding down. What about, I don't know, man. I gotta think about that some more too. What about like carryover and, you know, front is the most significant bit digit. Okay, the front is the most significant. Gotcha. You know, you have like carrying over, and then you have, what's the other one? Like if it's not divisible by 2, the value, right? The digit that you're looking at, which there's really only one, or no, sorry, not divisible by 2. Right, because division is basically, I'm thinking long division, right? I'm thinking applying long division to what long division by 2 looks like in base 10 and long division by 2 looks like in base 26. You, like if you had like, I don't know, 1100, right? You would divide, you would subtract 2 from, you wouldn't subtract 2 from 1, so you have to go to 11. You subtract 10 from 11, and that's 5. That's the number you get there. And then you have 100 left, and you recurse, right? And then you have what's 100 divided by 2, right? Then it's, you know, so I guess you could do it that way, right? You could do a recursive procedure. Base 10 works exactly the same, except you'd add 5 to the previous digit instead of 13. Yeah, so you're saying from back to front, though. You do back to front. I'm thinking from front to back. Because that's how I learned long division, right? So you would, whatever it is, divided by 2, some digit. If you couldn't divide by 2, then you carry, and I guess the digit you'd have there would just be 0. 0 is, I guess, marking digits that you don't care about. But you're saying from front to back, you remember that you will need to add the 13 after you divide the next one. So front to back, back to front. If you do back to front, if you divide by 2 back to front, you know if it's odd or even, right? Well, you need the remainder, right? So you can just remove the remainder if it's odd or even, whatever it is. So if you did like 501, right? Obviously, 501 is odd, so you take that 1 off, and you get 500, and you say, okay, digit divided by 2, we take that first digit, and you say you make it a 5, and now you're looking at 50 that you divide. No, I don't know, man. That doesn't seem right. I don't know. Long division in the other direction is not something I'm familiar with at all. Back to front, you already divided the next digit, so you can add the half to it right away. So the least significant digit, you're saying. So back to front, already divided the next digit. What do you mean back to front to back? Like, I'm trying to understand. Like, let me show you what I mean. So if you had like 501, right? Divide by 2. You get 4, 1, 2, right? 1 doesn't divide. 2 2 doesn't, excuse me, 2 doesn't go into 0 at all, or 1 at all. 2 doesn't go to 0 at all. Right. I don't think I understand. So you're saying, can you long division the other direction? See, that I don't really get, right? Because you would have this 1, and it would really just be 500. And you're saying something about a digit 5. I mean, do you just skip this 0? I guess you just skip 0. Oh, I think I understand what you're saying. Because you can go to 25 with this 0 here. If you just did like 50, you can go 5 and 2. Oh, that's interesting. Is that what you mean? You basically you would go through. Let's say if you had like 111 divided by 2. So clearly, you go to 110. Right? You already know it's odd, so you can take that remainder, lop that off immediately, and then now you have the 5 here. And then you'd subtract. You would. What's this 1 divided by 2? Doesn't work, so you have to go to 11 divided by 2. So it's still a 5. So it's sort of the carryover, right? Now you have 11. Which it's basically 10, right? You've basically already subtract this 1 off here, and so now that's actually it's 55. I think I get it. Let's do something else like 999, right? So boom, 998 divided by 2. We go to if we don't see anything less than 2, then we just go right to we go 4 here. That's actually divisible directly by 2. It's even, so you just do that. 9 is not even. It's still 4. See, that's the thing. I think you need to do the carryover. I think you need to do the carryover. Are you saying you just always? Because if this was an 8. This has got to go to 9, actually. It's 4 plus 5. Because this one, you have to check if the one ahead is divisible by 2 or not. If it's not, then you got something interesting going on. So here, it's not. So you take that 1 and you have half, right? The 5 here, and this becomes 4. And then you say, but here, same deal. This is not. So you also have to. This is also going to be 4 plus another 5 here. So you kind of have to. You got to do a bit of a look ahead at it, don't you? To see if the thing ahead of you is divisible or not. If it's not divisible, then you've got to add 5 to it. And let's see. And you're not going to have to worry about. You'll always be able to handle, because it's odd or it's even. You'll always be able to remove that remainder, right? So you're saying you do the same thing for base 26. You have some characters A, C, B, C, whatever it is. Right, and these are obviously 0, 1, 2. It's kind of interesting that 0 is its own character. That's a little weird. Maybe we can go, I don't know. You need a 0, right? Yeah. I think that's what's weird about it is that if you have leading A characters, maybe you should go to base 27 rather than base 26. Back to front, 158 divided by 2, 8 gives you 4, 13 being the 4 being the cursor, underscore being the cursor. 5 is odd, add 5. Are you saying 15 underscore 4? 5 is odd, add 5 to the previous digit. 15, 9. Then divide and round down. 129. 1 is odd again. And add 5. 179. Then divide and round down. 13 underscore should be 5. 15 underscore 4. Yeah, that's what I was thinking, right? Just the number after the fact. Right. I think I understand. I think I get it. Yeah, if it's odd or not, then you have to add the 5. Depends on the value to the left side. Yeah, it depends on the value to the left side. That makes sense. It's pretty interesting. Yeah, I guess you do the same thing too for, I'm trying to do it with, 2 is really C, isn't it? So this is divisible by 2. So you get 1, or yeah, but you gotta check what's to the left. Is B divisible by 2? It's not. So you gotta do 2 plus whatever 13 would be, which is half, right? And that gives you the 15th character, right? A, B, C, D, E, F, G, H, I, J, K. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that would give you character O. Q, R, S, T, W, X. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 3. I missed some characters, didn't I? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V. Missing a couple characters. Missing a couple. A, B, C, D, U, V, W. Bum, 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 bum. Bum, 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 bum. I don't know, man. I feel like maybe we should go with 27 characters, making this like, the null character. And the reason is that you want to differentiate between A, B, C, and just B, C, right? Like this would be 0, 1, 2, and this would be 1, 2. And these are not the same. Our hash wouldn't be able to know the difference. MN is the middle of the alphabet. So 0 is O is the 15th character, would be O then though. A would be 0 then though. Yeah, that's what I'm thinking. I'm like, I'm thinking maybe we should add another character so that A is not 0. And again, the reason is that whatever character we put in the front basically will represent no information, which is not true. I think we actually need 27 characters then if we want to do this properly. Because that's kind of what you do with 10 characters, right? You have 9 that are meaningful, 1 through 9, and then you have the 0, which is basically has no meaning. It's sort of a dead character. What's weird about that though is, yeah, you can't lead with 0 in a number. Like this is kind of a difference between strings and integers, is that we have 0, like 1, 0, 0, right? That has meaning, but we don't have like 0, 0, 1. And our hash should be able to handle like 0, 1, 0, 0, and 0, 0, 1, 0, 0. Should be able to differentiate between these, right? Because like A, B, A is not the same thing as A, B, A. Oh, that's some nice handwriting right there. Yeah, so that's kind of interesting. I think we probably would want to use one more character. Although there might be a way to do that without using another character, but yeah, make all these characters, and then base 27. Now you got to divide by 2 in base 27. It was hard enough if you have an even number of characters. It's like, there's some idea of what you can do. But if you have an odd number of characters now, what do you do? And then maybe you want to go to base 28 then, and just include another character, alpha, beta. So that way we can make alpha 0 and make beta a character we never see, but it's technically the 28th character. The reason is that we want to be able to divide by 2 easily. I don't know what it looks like if you have 27 characters. Well, if it's not, yeah, whatever the, it depends on this, right? So if you're odd, then you can just subtract 1, right? So this digit will always be, well, no, right? If it's I see. No, you always round down, divide and round down, right? So it's 27. I guess divide by 2 and round down. I guess it doesn't matter if it's 27 or not, because we're sort of always rounding down anyway. But that makes us a little uncomfortable, right? Because now we have 27 raised to the 18 characters, which is really 19, minus 1 divided by 26, which is only one more bit. So 86 bits we can use. Interesting. Very interesting. 86 bits, huh? Anyway, so yeah, I guess you could do what you're just describing to a similar kind of algorithm to divide by 2. Should be possible to invert the geometric sum formula. If you round that down, you can determine the number of characters encoded in that particular number. Invert the geometric sum formula if you round that down. Number of characters encoded in that particular number. Once you know that, you can use the geometric sum formula forwards to figure out the offset to subtract for the first word with that number of characters. Oh, I see what you're saying. In other words, don't use, save some space, don't use, it's only 1 bit, it looks like, by the way. I think we can handle adding 1 more bit, but if you get 7, you invert the geometric sum to get 0, so you know you have 1 character. And then geometric sum forward, you get 1, and you know that single letter word starts at 1. I'm so confused. Can you? What are you suggesting? I'm very confused. Well, the geometric sum formula is pretty simple, right? It's this guy. Oh. Like that's it. It's pretty, the proof is pretty neat too. You just say S equals 1 plus R plus ... R to the N. That's S of N. S of N plus 1 equals this thing. ... plus R to the N plus 1. You say R times S of N plus 1 is equal to 1 plus r plus r squared plus dot 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 r to the n plus 1, which is then equal to r to the n plus 1 plus s of n, then gives you s of n equals, oh no, yeah, r times s of n minus s of n, r to the n plus 1 minus 1, and then there you go. Booyakasha. Done. Ta-da! Hey! And this is s of n. Yeah. I really like that proof. Super succinct proof. But anyway, why do you want to invert it? What was the idea? For example, if you get 7, you invert the geometric sum to get 0 tilde. So you know you have one character. Then geometric sum forward, you get 1 and know that single letter words start at 1. 0 being the empty string, subtract 1 from 7, so you have the 6th one string word. 0th being A, so 7 is G. I am really confused. What? Basically the idea is to start at 0 and first encode all 0 length strings, then all 1 length strings in order, all 2 length strings in order, and so on. Why would you do that though? What are you trying to achieve? And also, what? Because I was thinking about my question was, should we not just use base 27 to make the math simple? But I guess you're saying you should do something else? No, I'm confused. Number of characters encoded in that particular number. Oh, I think I see what you're saying. So you have, I see. You don't actually don't have to invert it. You could say it's just 26. Yeah, I see what you're saying. Okay, I know. I understand now. You want to know the length of the number of characters required, basically, or how many bits you need. Maybe it's another way of expressing it. What the number is in base 10. Yeah, I think I see what you're saying. But that doesn't really solve the problem, does it? And idea is to efficiently encode all possible strings. Exactly 26 by 26 strings. So once you know the length, you don't need an additional symbol. And the start offsets are exactly the results from the geometric sum. Oh, I think I understand. So you're saying is because you know how many characters there are, like A, B, A, right? And then you have A, B, A, right? Because you know how many characters there are, right? So there's 4 characters. You can say, all right, that means our number is such and such a number. 26 raised to the 5th minus 1 over 4. Oh, wait. Oh no, 25 rather. So that's 47,255. 475,255 is the number. And then we want to know, I guess, how many bits we need. That would give us about 19 bits. So if you see 19 bits, that means you're dealing with, that means that these two portions where these characters would be, all those bits should be considered with regard to this number. Something like that, I guess, is what you're suggesting. I guess. I don't think that really makes a lot of sense. Reason being, the comparisons you're doing really are just bitwise comparisons to compare one hash to another hash. Like, you really do need something in these spots for these characters in order to differentiate them. Because the bit set's going to be, it's not going to be just 19 bit. I mean, I guess you could, since you only have 20, since all of your characters are only 20, since all of your words, you could actually segment this into hash. I guess you could do it that way. I guess you could break things down based off of the number of characters. So you do have you actually would you would take into consideration the size of the string. Yeah, okay, you do it that way. That works. Yeah, if you do also consider the size of the character, size of the string, 1, 2, 3, 4. And so now the bit sets that you're comparing for 4 strings are different from the bit sets that you're comparing for 1, 2, 3, 4, 5. And then you can still use base 26. However, then you have the added issue of requiring, you sort of have an extra parameter, which is the size of the strings, the number of characters. Yeah, you could do it that way. That's interesting. Neat. Then in that case, the bits in the front, these 0 bits, have meaning, right? Because you know they represent a character or a certain portion of a set of characters. That would work. Yeah, but you do at that point need to basically hash the hashes to the string size. In this case, we're lucky because the string size is small, so we can probably just make a vector of the hashes based off of, like an index into a vector of hashes, a vector of vectors of hashes. Excuse me, indexed by the size of the string. So that's pretty simple. But if you had like totally variable sizes, I guess. This would be really hard to do if you had totally variable sized amounts, though, because you wouldn't be able to easily predict. You wouldn't even be able to easily figure out this. Well, you could dynamically allocate the size of the bit sets. The bit sets, you can make them. You can do them with vectors rather than doing them with like a vector of booleans, rather than like a bit set, which the size of the array at compile time. But the problem with that is I'm not sure if you can hash. I think your hashing becomes kind of a little weird. It's not really a hash anymore. It's really just a 2-bit vectors that you're comparing, and then your comparisons are like you have to loop through all the bits to compare them to see if they're the same vector booleans as the same ones. That's a very interesting question, though. Like, I'm definitely get my noggin a jogging here. Definitely get me thinking. Got me thinking. They're exactly 26 by 26 strings. So once you know the length, you don't need additional symbol. And the start offsets are exactly the results from the geometric sum. It's true. It's true, but I don't think you even need the geometric sum starting points, right? Because if you know the length of the string, if you're operating on that, then That's all you really need. So if you can invert the geometric, you know the expected length and can remove the offset before decoding. Oh, I see what you're saying. So given some x, you want to know what the length is. Length n being n. Yes, you would do 25x plus 1 log base, whatever. You can just do log whatever base you want. Just change a base to, and then by the way, subtract 1. Wait a second. Sorry, hold on. We'll use natural log. Add 1, multiply by 25. Take the natural log. Oh, yeah, I had it right the first time. So this tells you how many characters you're going to need to store that particular number. And you're saying this is how you can get the different boundaries. You actually don't need to invert anything for this, by the way. This is so obviously geometric sum is just, it's 26 raised to some power, usually goes up to how does it work? It's raised to some power, actually. That's it. It's the bounds are like, it's a few things. So what you have is it's kind of neat how this works, but basically you have a number that ranges from 0 to 25. You have some power, right? These different powers, and you have like sort of alpha 1, alpha 2, alpha 3, which are literally the characters, the symbols, right? That's the sort of what they represent, is sort of groups of powers. And if you wanted to know, like, okay, when do I need the next bound? When do I need, when do I need another character? Well, that's actually exactly when you want to represent this number with something more than a 0. And you'll find that actually if you add all these numbers, they are, that sort of, it comes out in the geometric sum formula that when all these are 25 times 26 to the first plus 26 squared, oops, plus 26 to the third, plus 1, or that is exactly equal to 26 to the fourth minus 1. Right, and that's what we had before. That's r minus 1 times the sum of I equals 0 to n of r raised to the I is equal to r raised to the I n plus 1 minus 1. Right, that actually is the geometric sum formula. So once you sort of filled up all of these characters, that's when you need the next one, is actually exactly when you want to represent 26 to the fourth. So it's every power of 26 is when you need another character. And right before that would be sort of just subtract 1, and those are the bounds. So you actually don't need to invert anything. Hopefully that makes some sense. It's kind of a nifty. So yeah, the expected length, I guess, between each is basically 26 raised to the x plus 1, and all the numbers up to 26 to the x. Those are, like, this would give you the range. It's the number of characters that require x would be, or that require, yeah, I guess x characters is exactly 26 to the x minus 1, or x minus 1 characters rather. So it's the number of numbers that require x characters to represent is 26 raised to the x plus 1 minus 1. No, excuse me. The number of numbers that require at most x characters to represent. That's what it is. At most x characters represent. It's 26 to the x raised to the x plus 1 minus 1. Now you subtract all of the numbers that require at most x, and you get exactly what you just saw here. If you subtract all the numbers that require at most x to the x minus 1 characters, that means that you are now looking at all of the numbers that require exactly x characters to represent, and that's this difference, which unsurprisingly is exactly this expression. No, yeah, which is then this expression for any particular x. It's, which is kind of interesting. And you can see the similarity to this formula here. Very neat, very interesting. Yeah, as soon as you need that next character. Well, yeah, I guess that's, yeah, anyway. All right, enough of that. Messing around with offsets and whatnot. Let's go to the next problem here. So I forgot what we were talking about. Word pattern 2. Okay. Is that right? Did I get the yeah, I completely forgot why we were talking about all that. Well, yeah, it's pretty interesting way to, I guess, not, yeah, you can write a hash instead of storing the words to save a little bit of space, a little bit. I don't know if you save very much time after that, though. I think the lexicographical search is probably faster than converting these things to hashes and then comparing the hashes. Probably. Could be wrong about that, but probably. Anyway, so word pattern 2. Given a pattern in a string s, return true if s matches the pattern. A string s matches a pattern if there is some bijective mapping of single characters to strings, such that if each character in pattern is replaced by the string it maps to, then the resulting string is s. A bijective mapping means that no two characters map to the same string, and no character maps to two different strings. Okay, so pattern in a string S, return true if S matches the pattern. A string S matches a pattern if there's some bijective mapping of single characters to strings such that if each character in the pattern is replaced by the strings it maps to, then the resulting string is S. Oh boy, that's a mouthful. I can think about that. I want to say this is probably similar to like a regular expression or a string search. Some variation of these things. I'm not sure though, this might be slightly different. A bijective mapping means that no two characters map to the same string and no character maps to two different strings. Pattern A, B, A, B, S, red, blue, true. One possible mapping is as follows: A red, B blue. Oh, this is totally different from string search. There's stuff like what do you call that? Knuth-Morse, KMP, the Knuth-Morse-Pratt algorithm for string search, that in theory, I think I could in an interview basically like recite the algorithm from memory. I don't know if I can though, and I practically though. I don't know if that's true. It's kind of hard, but it's a pretty interesting algorithm nonetheless. But yeah, building the lookup table, I think. I don't know. I have to do it a few times before I could say comfortably that I can do that sort of on the spot. By the way, today is Thursday. Nice. Friday. Tomorrow's Friday. I'll have the weekend to not have to go to my job, which is nice. So one possible mapping is as follows: A to ASD. Okay. A, B, A, B. A to A, B to ASD, ASD. Excuse me. Or that A and B cannot both map to ASD since the mapping is bijection. Okay, it's bijective. Gotcha. Pattern A, B, B, X, Y, Z, A, B, C, X, Y, X, Z, Y, A, B, C, false. Now this is an interesting question. I don't know the answer to this offhand. This is, I mean, not to say that the other questions weren't interesting, but this is, those questions were more interesting because of, I guess, the encodings that we were thinking about putting together, the hashing basically. But this is more interesting, just the inherent problem is challenging. So pattern length, string length, pattern and string consist of only lowercase English letters. The string is pretty small, that's good. So maybe we can brute force this, but this seems like kind of a hard problem. I gotta like think about this for some time. So bijective mapping of single characters to strings, like A to red, B to blue, such that if each character in the pattern is replaced by the string it maps to, the resulting string is S. Bijective mapping means that no two characters map to the same string, and no character maps to two different strings. So what's interesting about this question basically is you have to show that no bijection exists to match that pattern. That's kind of what you got to prove in order to show that it's false, or basically give the bijective pattern to show that it's true. And that's where we're at here. And I'm also going to charge the headset here. Yeah, this is interesting. So forgive me, you're going to be hearing this noise now. So, okay, let's think. Oh. Excuse me. Oof. All right. So these bijections. Well, you could consider it kind of like a kind of partitioning, I suppose. There's like a few elements here. I guess the first thing I think of is actually like the number of characters that you need to have. But it's not even just the characters, it's actually the type of characters also matter. In other words, it's like it's literally a pattern. It's not just the size, but it's also the sequence, the content. Well, I guess I'd have to think about it for some time. Well, going through some examples usually is pretty good. It gives you an idea of, like, you go through some examples and you think, all right, how could, an example that clearly doesn't work, why doesn't it work? So I think you had AA, BB, and XYZ, ABC, XYZ, ABC. So I don't actually know why. I think the reason that doesn't work is that any possible substring that you could use for A or B, firstly you could check by the size of the string. Excuse me. So if the size is XYZ ABC, you need to have 12 characters, the whole thing, right? The whole thing's got to be 12 characters. And that means that your bijection, you have 4 characters, 12 into, and they're split amongst 2 different characters, 2 different pieces, each. So it's 4 characters, or rather, yeah, two different characters, four characters total, 2 different, I guess, character values, and that means 12 has to be split into 2 pieces that are both divisible by 2. Also, not only is it 2 character values, but also each character value has two characters represented. So you've got to have 12 split into 2 different integers, both of which have to be divisible by 2. And evenly divisible by 2, or just divisible by 2. So that doesn't give us too many options, right? You have 1, 11, 2, 10, or they have to be even too, right? So it's going to be, you can have 2 and 10, 4 and 8, and 6 and 6. And that's it. That's all you got. You only got these 3 options for possible sizes of values. And what are the options for those things? Oh, excuse me. Right. And obviously divide all those by 2 to give you the actual amounts. So it's really 1 and 5. What did I say? 4 and 8. 2 and 4. 1 and 5. 2 and 4. And 3 and 3. So those choices. Sorry, I'm kind of falling asleep here. Really tired. my mind is wandering a bit. Sorry. Falling asleep. Okay.
Actually, I think I forgot what the original problem was now. Went so far in different directions. Forgot what we were even thinking about now. Yeah, I forgot what the original question was now. My mind has gone to so many different subjects. What even was the question? Wow. Oh man, I laid down for like a minute or two and boom, I think I fell asleep, or practically fell asleep. Again, I'm trying to remember what even is the problem we're working on. Oh, I remember now, yeah, we're mapping characters. Right, bijections. Yeah, I just like knocked out. So I laid down, I forgot where I was. Oh. I do need to like take a break, get some food soon. Maybe take a nap. But man, I must be like laying on a nerve or something because my left hand just goes numb after I lay down for a while. A certain position just goes out. I don't know if it's blood or if it's a nerve or something's getting pinched. I don't know what's going on. Well, I guess one way to look at this problem, I think, yeah, I was supposed to think of just some naive approach to solve the problem. So a naive way would be the first string you see, the first character. You could map sort of any string that also begins, any size string that sort of begins at the so there's that pattern, there's the input string, right? We'll call it the input string. So what do we call it? XYZ ABC, right? So that input string, XYZ, XYZ, or XY, XYZ, XYZ, ABC. For A, there's all these possibilities. The only one that's even possible, because as soon as X ends, or as soon as A ends, A begins again. And we can see XX doesn't match, it can't be the beginning of the string. XY can't, XYZ can't, XYZA can't, etc., etc. There's actually just no possibility for even just AA to be a pattern that could work. So we can kind of eliminate that out the gate. Yeah, interesting. So just thinking. I actually am. I'm starting to think maybe just like I'm just thinking of any solution at all that would work. Just a naive solution. I want to say a depth first search is the way to go. You pick a string for A. You know, pick a a length and character set for A. An initial string. And then the next thing following it right from A, then you have B. You pick a possible string for B, and then if you've sort of what do they call that? If you've selected all of your characters for your bijection, then check to see if that works, and if you have to select more, then continue selecting more. But I think obviously the order, the strings of characters that you pick for I guess the strings and characters that you pick need to be in order. So for A, you start with the first letter, and then immediately you could see, well, it can't just be the first letter because you'd have to have AA, and the next letter doesn't work. So I guess you have something like terminating early, but yeah, I guess the choices begin with sort of from left to right until you encounter the next character. You sort of have all these copies. There's kind of a lot of conditions that sort of make a certain possibility not possible, but I think a depth first search at least covers everything. The problem with that, though, is I'm not sure how expensive that would be. Now, granted, these strings are really small. I mean, these strings are, they say string size 20, and I think the patterns themselves are only less, between 1 and 20. So really shouldn't be a problem to use a depth first search. But something you kind of want to avoid if you can, right? Because that's exponential time, basically. Yeah. So it's pruned, but it's still a very expensive algorithm in theory. So I think that's it. I think you just have to kind of brute force it. I think it's the only option we have. An exhaustive search, or kind of exhaustive search with sort of pruned branches, we'll say, in the search tree. I want to say that's what we're going to go for. Also, forgive me for having this background noise because of the headset charging. I think I'm going to pull it off now, don't charge it. Yeah, I think I actually fell asleep and realized it, but I kind of somewhat wore myself out, kind of tired now. I want to think about this here, so How do I formalize this algorithm though? I'm having a hard time even describing it. So the first choice would be for the first character of the pattern. You have sort of an arbitrary length of the arbitrary size of the beginning section of the string, the input string. And you put that as the first possible choice for that character. And then the next thing that happens is, you have the next sort of arbitrary length, right? Sort of it's a depth first search. So the next character, now, if it's the same character in the pattern, then obviously you can terminate early as you're sort of selecting the length if it doesn't match, right? So obviously you have. So I guess the neat thing is that if you have if it's the next character in the pattern isn't a character we haven't defined yet, then you can check to see if what we've selected there currently fits, currently matches. If it does, then you can continue and look to define the next, sort of scroll forward past that portion of the string to select the next character. Yeah, select the next the next character in the pattern. Select that character's string, associated string. Right. So yeah, being a depth first search, it's as simple as you have a really just a size that you're working with of string. And I guess you could take I guess the state of the depth first search would be just an unordered map where you have like a string mapped to a particular character, so you could just look it up quickly and see what did we already select, and if there's nothing selected yet, then we get to define it and recurse on the different choices. And how many choices do you get though? Well, you don't really terminate too early, I guess, because yeah, that's kind of a tricky thing, is that the loops that you're dealing with, I think they loop for the size of the whole array, really. I mean, not quite. You kind of have to consider how many characters are possible that are left. So maybe you can kind of know the length that you're working with based off of, I guess, how many characters are already defined and how many times those characters show up in the pattern, and how many characters are in the string that you're looking to, the input string. So you can kind of reduce how much searching you do, but you don't terminate early in the loops, which is kind of interesting. You actually, in other words, like if you had x, AA for the pattern, and you had some string, as you find characters that don't work, you actually would increase the possible size for the initial string A until it does work, I guess. Yeah, and I guess the whole thing is just a recursive search for, there's sort of a true or false, I guess. It's not even true false. I mean, you just push the state, that bijection, you push that on into, like, it's a return. I wouldn't even what do you call that? I would actually return true in my Boolean value to terminate early once you found something that's a mapping that works, and then return that mapping, and have sort of part of the state be defining that mapping. And I guess return false every time that you hit a case where you can determine logically that it won't work anymore. I think a depth first search is all we want to do, all we can think to do. I'm really tired. I didn't realize how tired I was. I probably, you know what I think I'm going to do? I think I'm going to look to code this one up here, a brute force search, and then go take a nap, make some food, take a nap, relax, probably go to bed. Because I'm exhausted. I didn't realize how tired I am. I have been having a hard time sleeping lately. There's like a whole mess of stuff going on with me right now, lately. Nothing severe. I don't want to say nothing medical, but I'm not really getting enough sleep. I'm also not adjusting too well to the colder air. Winter time has come. The dry air. Oh man, I'm sorry. I'm like just falling asleep. That seems to be the problem. I'm just really tired. I'm not even thinking about the problem right now. I'm thinking actually about all the other things on my mind, all the other things on my plate, all the other things to think about in life. Except all of the other things in life to think about, except the problem we're working on. Alrighty. Oh, okay. But yeah, I mean, the thing is with these problems, I've kind of reached a point where I'm kind of expecting that I would solve them all very quickly, and I guess I'm somewhat disappointed because I'm not actually solving them all that quickly. Again, I think in this case it's probably just because I'm really, really tired, and falling asleep. But yeah. Excuse me. Medium seems a bit strange here. I think standard mismatch will shine in this one. Oh yeah? Oh, I'll take a look at that. I won't be able to cope with full 20 characters. That's just up to adjusting the storage capacity of the type used. We wanted to store lowercase words as efficiently as possible, so we'd streamline comparisons. Hey, that's fine. It doesn't make sense to try to attempt this falling asleep. It'll probably work out much better after a good rest. Thanks. It's good getting late here as well, so I'll be heading off too. Thanks to stream. Yeah, take care, Simon. Thanks for hanging out, saying hello. I appreciate it. Thank you. And forgive me, I didn't read your comments for a while because I laid down. Mismatched. Yeah, what's standard mismatch do? Also, let me just check something here. Okay. Let's see. Medium. I
I mean, I guess not too bad. Only 20 characters, I think is not too bad. But algorithm. First range of elements, second range of elements. Execution policy to use. What is that? Binary predicate returns true if the elements should be treated as equal. Pair with iterators the first two non-equal elements. Interesting. Oh, huh. It's probably like this. This is probably better. But anyway, oh really, it's that simple. It's just two ranges and then a predicate to compare the values in the ranges. That's kind of neat. What's an execution policy? What's that? Disambiguate parallel algorithm overloading and require that a parallel algorithm's execution may not be parallelized. Invocation of element access functions in parallel algorithms invoked with this policy usually standard execution sequence are indeterminately sequenced in the calling thread. Execution policy type uses a unique type to disambiguate parallel algorithm overloading and indicate that a parallel algorithm's execution may be parallelized. The invocations of element access function in parallel algorithms invoked with this policy usually specified as par are permitted to execute in either the invoking thread or in a thread implicitly created by the library to support parallel algorithm execution. Any such invocations execution in the same thread or indeterminate sequence. Oh, interesting. So you basically tell whether or not the algorithm should be parallel or not. Oh, that's kind of cool. It's part of the STL algorithms. Oh, cool. That's kind of neat. Where's the P is policy? No, before the P. Policy. There it is. Okay. So if you want to give it a policy, you can give it a policy first. Oh, and there are different. Oh, interesting. Okay, I see. There's different variations of this. This is sort of the one that I would typically look at. Same as 1357, but with a policy. Use the operators equals, use a binary predicate, and then some of these use first last and another first last. Last two is not provided. These overloads denotes first two plus last minus first one. Right. I guess it's just automatically you get this last two is just automatically generated. Huh. Really interesting. Okay. Cool. That's useful for Oh, you're still here. Hey, what's up, Simon? Hey, welcome back. I appreciate you still hanging around. Basically allow us to check whether an already expected pattern will match the upcoming characters with correct boundary checking, and if it does, it will return the start point for the next pattern. Oh, interesting. Allows us to check whether an already expected pattern will match the upcoming characters with correct boundary checking, and if it does, it will return the start point for the next pattern. Oh, you're right. Yeah, that would be pretty good. Yeah, you can use the iterator instead of using Oh yeah, that's actually makes it a lot more concise. Instead of what do you call that? Instead of, let me think. Right, yeah, using iterators is better than, instead of using, well, for starters, yeah, I guess the other way would be to use indices and compare directly. Basically, you write a, oh yeah, this is really good. Thank you for pointing this out. I don't really spend too much time in the STL. I appreciate when folks kind of point out different STL algorithms that would be useful, because I don't really use it too much, you know. I just kind of like solve the problem whatever way I think I can or should. And yeah, definitely mismatch would be very useful here. True. Good point. And actually, hold on. This will give you. Whoops. This will even give you. If you get all the way to the end, that means that you. That you. Really, I think actually want probably equal. Don't necessarily want the mismatch, but probably just want equal. Or you can do mismatch, and if they don't mismatch, if you, well, let's see. I think equal is probably the one that I want, actually, when I think about it. Let's see. Okay, so how do we do this? All right, let's do a depth first search. So auto DFS. Gonna do some things. And we want to say, so we're gonna have a map. I'm gonna organize my thoughts as I program it. I think a character, and we'll use a string. I think. And oops. And I want to say, just call it bijection. And we're going to have a few things here. So we're going to store the state in these kind of like somewhat static, not really static, but pseudo-static. These, call them local variables. So let's do it this way. Let's say string iterator. I think we can do that. And it's going to be sort of next character or next pattern. No. I want to say like next pattern character, something like that. And we'll do also, these are not going to be modified at all. So let's just add that. I don't really make everything const that should be const, truth be told. Whoa. I didn't mean to do that either, whatever I just did. Next pattern character will start at the pattern beginning. And we'll say, also that's not correct. We want state of the bijection, and then I guess what we return. Oh, actually, yeah, okay. Really, this could just be, oops, a couple things here. Yeah. I don't know if I even need, how much of the state, I don't know if I even need inputs. So, we do want iterators. Yeah, we do want iterators. Yeah. Mm, what are the input iterators though? I guess it's just where we are in the pattern, and then we don't really even need that, do we? Just thinking. Interesting. Yeah, I think everything in the state we can just kind of, let's see, and then just the next character, or just current. I'm not really sure what I want to call these. Really like the algorithm library. Yeah, the algorithm library is pretty awesome. There's a lot in there. There's a lot in there. Check whether the expected pattern will match the upcoming characters, and with the correct boundary, checking if it does, it'll return the start point for the next pattern. Right, that's true. Yeah, you're right. Although it also does something kind of, yeah, I'm not gonna say anything. I'll just say it could be useful. I'll just say it could be useful. Okay. And we want to say, really it's so base case, if we want to say which character, so character, so I guess first things first, if next pattern character is equal to pattern.end, I think we're done at that point. I want to say something like that. We can make it really simple, I think. I think we can make it really simple, like this, super simple. We can do a for loop. I think that base case could be that simple. So for I guess what I want to say is now obviously we want to make sure if we've used all of our, if we came too short, we want to return false. Not entirely sure how I want to do this. It's a for loop. We basically want various different sizes for C. So we would say if bijection of C or bijection.count of C, if this already exists, then we're going to go ahead and say standard equal of it's going to be current to it's going to be current to current plus it's going to be the length of bijection of C. So we're going to say just string, we'll call it. Or we can just call this X. Really, it's the size. Current to the size. And input first. First, last. We should be able to do 4 of these, right? Yeah, like this one. Do S and S plus X dot size. Right, that's pretty much what I want to do. I want to see that this bijection, this current position in S, and we want to see this bijection X dot begin and S dot end. This is number 5, right? Yeah, I mean, pretty simple. So I've already defined this character. Then we want to check and say, we'll just say if bool check, if not check, return false. Otherwise, we're going to call f of f. We're going to return f of f, right? Can actually just do return this check is true and f of f is true. No, you want to not quite. Yeah, otherwise you want to actually set current to current plus x dot size, and then you want to set C or next pattern character plus equals 1 or advance 1. These iterators are random access, so I think we can use these just addition operators. Now we're not going to, this isn't going to be necessarily recursive. It's recursive, but it's not really recursive. It's sort of like tail recursion. Sort of just continue to skip over these patterns that we see. I think that's what we want to do. So we have this check, and if we fail the check, then we return false, and that's the end of it. But if we don't, then Current size, next pattern. Yeah, you want to go to the next pattern character. And return F. Now, if we don't have a bijection defined, now we have a whole lot of choices that we can pick from. So we can say this is basically going to be the size that we select from. We'll call it I. Size 1, 2. Now here's the thing. We don't actually know how big of a size we want. Don't actually know how big of a size we want. There are a couple, I guess, optimizations here. I would say something like once you know how many strings, how many characters are in the pattern, and that once you've defined a character, then you know how many characters are sort of already defined there. Just thinking. I want to say there's like a certain total number of characters that you can keep track of that you haven't used yet, based off of, I guess we create a frequency map for each pattern that we select, and that gives us at least some bound on how large we can make each of these characters. It's kind of awkward. Also, there's a problem here of like, well, I just think. Could do this. The sizes, the possible sizes. Really, it's got to be. I mean, we could do it. We could do it this way, I guess. Keep it simple. I guess it doesn't really matter that much if we just throw that bound in there. We just want to say I is going to be less than the s. It's going to be s dot end minus current, right? And probably minus whatever you're currently looking at. The end, let's say if you have, that's sort of the size, s dot end minus the current is sort of the size minus whatever index you're looking at. So the size is 5 and your index 0. 5 minus 0 would be sort of the size. I is less than the size, which is 5. It actually, I is a size itself. So we actually want something like this. And we'll just keep it simple, this bound. And then we say each of these possibilities basically we set bijection of C equal to I guess the substring, which I think we can get a standard substring, right? That being said, I think I may have found my footing just now. Oh yeah? I'll just try a few more minutes then. Fair enough. Sure. Fair enough. Yeah, possibly. Possibly. I'm looking for this substring method. I think it's just sub. Oh. Isn't there a way to get a substring? You can actually do something slightly different, which is instead of storing the strings in this, I kind of would prefer to just store the strings directly, but because these are small. I mean, this is like really small. But you could actually store a pair of iterators as well, which represents the string. But there's a way to substring, which I don't remember. Substring, yeah, there you go. Sub str and just position and amount, and that's it. Position amount, there you go. So substring of s, and we want the position is going to be an integer, and which is going to be, the amount is I, and the position is going to be the index, which is its current minus s.begin. Right, so this is pointing the first value. I think that's right. I think that's what we want. So I'll set the bijection there, and then obviously erase after the right. So this is the pushing and popping onto the stack. So you set the bijection, call f, and say ret or equals f. We actually want to do better than that. So if we see, we want to terminate earlier than that. So we just say if ret, then return. Just immediately return true. Don't bother with the rest of the loops. So we set our bijection. We also have our current. We want to save that temporarily, so we'll just call it auto temp equals current, and then current equals temp. Gonna reset these states. Next pattern character, temp 1, temp 2. Next pattern character, yeah. Yeah, these three things need to reset their state back to where they should be after checking each of these things. And I think that's really it. It's not that complicated. Oh, yeah. Yeah, that's pretty much it. Oh, we do want to update current to, we do want to do that. And yeah, that's okay. By the way, we don't just want to we don't just want to set these and then undo them, because this is going to mess up those parameters quite a bit potentially. So we want to save them on the stack and then reset them. So I want these auto values. So we do want, right, where we are in our string gets updated with the substring. We basically just assume that matches and move on. Wondering if there's anything else we need to check on. I feel like I'm missing something here. I don't know. Could just run it and see what happens. Tempted to do that because I don't know. Just want to see what happens here, I guess. If it compiles or not. Really? Please? Is that because, oh, it's probably because this is const. That's probably why, yeah, okay. Even though those should be const. Oh, it worked, whoa. No kidding. What? It's really that easy? No way. No way. No way. No way. I guess I'm just getting better at this. feels like that shouldn't be that easy. I always feel like I missed something, you know. Okay, runtime error, nice. Okay. All right, good. Good. Ran into issues as expected. With questioning things if it don't run into problems. It shouldn't be that easy. There's no way it's that easy. Do each one of these one by one to find the one that's causes issues. All right, it's the one that fails. The one that fails. Runtime error, stack buffer overflow. Nice. Okay, why? Is it just like it's a buffer overflow, so do we just never stop recursing? Is that what happens? I don't know. What happens? It must be just like an infinite number of, I don't know, 1 through 9, and then what? Let me see something here. What? Okay, so we never get past the first. Interesting. What happened? So we did call each of these, and then we got these two, called this one, and then we called it again, another one, and what, 5, 6, 7, 8, 9? We got all the way to 9, somehow. feel like I'm really taking a lot of time here. I don't know, I guess with things that you're unfamiliar with, it'll happen. Where does this runtime error occur? Is it this one? No, 3 is fine. 0, 1, 2, 3. On the B, is it here? What is? Yeah, I think it is. I mean, I don't know what's going on. I must have missed something along the way. Test 1, we didn't get to test 2. So this actually caused a problem. Oh, no kidding. Test 11. Test 11, excuse me. Pass some gas. Ah, so the equals check is what causes the problem. No kidding. I was not expecting that. Well, I guess it would be... Oh, I didn't really think about that. I guess it should be this. Nope. Still run into problems. Oh, I think current... it's not s.end. Hold on. Let's see one. Let's see one. That's the one we're looking at. Oh. Oh, no kidding. Okay. So this actually assumes the full range. Okay, that's kind of what I was thinking. Well, what if these ranges are not equal? No. True if this range is equal to this range. First 2 plus last minus first. Oh yeah, no kidding. That's awkward. So actually, I need to add a little piece here. Gotcha. Gotcha. All right. That would make sense as to why I'm having problems here. Couple things. We want to say current.end minus current is basically if kind of want to do this. I want to clean up the. I don't really like the. What do you call that? The. I don't really like this going off the side of the screen like that. I was wondering what was wrong here. Okay. Current.end minus current is got to be that size. It's got to be greater than or equal to x dot size. Basically, this range needs to match, match here. Need to have enough characters, like really simple. So I think one problem would be actually let's just run that. Well, I don't want to just run it. Let's think that through. Let's do the math, right? We should be able to do that kind of quickly. The maths on this. The size, the end minus current. If current is an index 3 and there's 5 characters, 5 minus 3, it's as if you did index 6 minus 3 to get the number of things between them, but add 1, so it's the number of things between them and including them, but then remove that last one. That's so confusing, but yeah. And then also remove do you remove, no, my question is, do I subtract 1 again? That's kind of what I'm wondering. Compiler error. Oh. Okay. So it works correctly now. I'm just wondering if that's dumb luck that I got this right. So you're at the end of the iterator, end of the string minus the current iterator's position. Let's say the current iterator's position index 2, end of the string it's sort of 5 plus 1 would be 6. It's 6 is sort of, it's 1 after the end. How many things there, the number of characters we want to include 2 but exclude 6, but include 5. So you'd subtract 1 from the end to make it 5. You subtract 2 but then add 1. Yeah, that's why it's so confusing, but it's b minus a plus 1 minus another 1 because b is already off the edge, right? That's the way to reason it. Yeah, okay. So that seems right. So I guess that's it. I guess we solved it. Took a really long time though. Really could have done that faster, I think. Didn't really need to think that hard about it. Let's just try again. Yeah, depth first search is good. Good way to do things. Oh boy. I'm afraid, dude. I want to throw in some random test cases. Let's see if we can throw in test cases that'll break this. Okay, we gotta be at least 1, so both of them are at least 1, so that's good. Let's just try some gibberish. And more gibberish. See how that goes. Let's try another one that doesn't work. Alright, that one should. Oh. This one's kind of just gibberish, but made a mistake. see if we can. It's true, and then let's put like a Z in there. I don't know, I'm just trying to test different things to see if I can get it to fail. I don't know. All right, let's go for it. I don't know. There's got to be some test case I'm not thinking of. Oh, come on. A, B, and AA. Really? It seems so. It's always those really simple ones. I don't know. I wasn't even thinking of that. All right. True, false, false, false. These two, bottom two, A, B, and AA is the one. All right. Well, I didn't get it. I don't know. I'm not sure what I should have done differently. I guess test more test cases. I guess. What did we do? What happened? They can't be this. Oh, it's a bijection. That's why. Oh, that's such a subtle. That's such a subtlety. Nice. I'm still typing out the first version. Nice. Yeah, there you go. I just wanted to say I didn't even hand it in a single time. I didn't even hand it in a single time. Completely forgot that this is a premium problem. I'm solving in one box instead. Oh, I'm sorry. I'm sorry, man. I feel guilty. I feel bad. I don't know what to say. I'd say I'd buy premium for you just so you could test it, but I kind of need to save money. I know I mentioned that earlier. I lost a lot of money trading. A lot. I really shouldn't be spending money willy-nilly. Speaking of, just want to see, check. Don't feel sorry for me being cheap. I wouldn't say it's being cheap. It's more just, I don't know. It's just kind of unfortunate, I guess. Wait a second. Oh no, I would have. Oh, no kidding. So I'm just checking something. Give me 1 minute. Now that we're on the subject. Uh-oh. Wow. Huh. What, oh, that's not good. Sorry, just give me a minute. I'm sorry. I'm not sorry. Just give me a moment. I don't want to say I'm sorry if I don't mean it. No kidding, really. That's what happened. Wasn't expecting that. Alrighty. Huh. Well, anyway. Yeah, forgive me. Or not forgive me, but it's good for that. Alright, so, because it's a bijection, that's why. You just have to make sure that there's no other, other strings already. This is the range, right? Let's not use that. Let's use a different phrasing. We'll call this not output, but what do you want to call this? This is the What do you even call these? It's sort of like the range, not the domain, but the range. That's what I want to call it. I just want to call it the range. Just already seen something, already selected. It's probably better. Already selected, so you can say standard string s, or not s, sub. And we'll say if already selected dot count of sub is 0, or we could just do this. We'll continue. If it's already been selected, we just continue. Otherwise, we set this bijection to sub already selected dot insert sub, and then we want to remove sub. I think that's what we got to do. Something like that. There we go. All right. There's probably another test case that I missed somewhere, but we're just gonna go for it. I don't know. I don't think I'm gonna think of it. I'm kind of ready to move on to the next problem. If I missed it, just more than possible. Let's see. Oh, got there. Hey, pretty quick too. Pretty fast, efficient. Not bad. All right, it took forever for us to solve this though. How long did we spend that on that? We fell asleep too, right? 3 hours. Oh boy. No kidding. That wasn't too bad. That wasn't bad at all. Kind of rough though. A few things. One, obviously falling asleep. It took me forever to code it. Messing around with the bijection was kind of tricky. Definitely not too bad though. I wouldn't say it was a really hard problem. I would say it's relatively easy, you know. Pretty nice that it's, you know, it's only 20 characters each. Obviously this gets out of hand really quickly. I like problems like this, but I'm a little disappointed in myself, I guess, because like I don't know, I just feel like it took a lot longer than I should have. This is the kind of thing that like maybe 30 minutes, you know, once you realize. But I guess that's part of it. It's like I don't know, I kind of don't have enough practice with these like really, I guess, unusual questions that are sort of like kind of can only be done with I guess backtracking or depth first search. Yeah, these are kind of challenging. Kind of challenging. Yeah, I definitely got tripped up by a few different things. Trying to use the equal, I used that incorrectly, and then that tripped me up, and then actually failed not paying attention to the range, sort of what the bijection was already set to, and then I also just kind of thinking about how we could set up the depth first search kind of tripped me up pretty badly too. You know, here's this portion to skip the sort of the parts you already set, and then this portion to set up the state and then reset the state. I mean, this really isn't that complicated. It just I don't know, for whatever reason. I think I got stuck on these pieces too, like figuring out how many characters we should have. You know, how many characters we should range over. How to exit the base cases, certain cases. All these things kind of slowed me down quite a bit. But this is good. I mean, I think if I saw this question again or something similar, I'd be a lot faster now. So that's good. That's good. But yeah, let me go. I think that'll be it for me tonight. I'm going to go finish my food and then probably just go to bed, take a nap, go to bed, something like that. Let me, there was something I wanted to do. Oh yeah, I checked. Yeah, I lose money. I lose money trading. That's that's it. I just lose money. It's sad. It's sad. Yeah, I lost a lot. It sucks. It sucks. Anyway, okay, let me go. So thanks again, those of you came by, said hi, watched. I appreciate it. I'll talk to you all soon. I don't know what I'm doing next. Yeah, probably just going to bed. Yeah, have a good rest of your day. Have a good rest of your night.